Welcome to our next video in the series on condensed matter theory. In the previous video we derived the Hartree Fock approximation where we showed that we find an eigenvalue equation for the one particle orbitals that have to fulfill that H1 plus 4 terms related to the Coulomb energy, the direct and the exchange term, times the wave function or integrated over the wave function have to be equal to the eigenenergy times that wave function. And the orbitals that we have in here, the psi's, are the eigenorbitals of the Hartree Fock equation, such that we are looking for a self-consistent solution that we have to iterate to self-consistency. We can write down the Hartree Fock approximation on a basis of general orbitals, such that we then have to solve that Hamiltonian. And this is the best done within second quantization, where here the Hartree wave function is always given by a single Slater determinant. When we go to a general basis, that is no longer the case. We can make a rotation that it becomes a single Slater determinant, but the general solution must not be a single Slater determinant. So we have in second quantization the energy coupling state 1 and state 2 by the one particle Hamiltonian. And we have the Coulomb matrix element Ij KL given as a half psi I R1, psi j R2, H12. Note that sometimes this half is included in the Hamiltonian, such that you don't see it additional here. This Hamiltonian is E squared divided by R1 minus R2 instead of a half times it. Psi L R1 psi k R2. Note that in our definition we have R1, R2, R1, R2, I, J, L, K when we have here the normal order. So it is I with L and J with K that is interacting. So these two relate to the same coordinate and the outer two relate to the same coordinate. Then we can write down our Hartree Fock Hamiltonian as a sum over Ij, and if we look at our first term, this is just the Hamiltonian times an orbital, so that becomes epsilon Ij, or the Hamiltonian times a one particle state. Sorry, in atomic theory we're used to calling one particle states orbitals, which is a language that one can adopt also in general. So sometimes I call one particle states orbitals and you can just freely exchange them. I'll try to keep with the one particle state definition. A dagger I, Aj. And then we have the two particle interaction IJKL, UIJKL, where we have here an expectation value between two states, and on a general basis that is A dagger I AL times the expectation value A dagger J AK. And in the second we have just exchanged about which elements we take the expectation value AI, AL, and which we leave as an operator. And then for exchange we have the other two indices that we have to either take the expectation value IA, AK, A dagger J, AL minus A dagger I, A K, and then the expectation A dagger J, A L. Now here you're not allowed to sum over two states with the same indices, so we have to also subtract that here because we did not include that so far, and that is the expectation value AI, AL, A dagger J, AK, and here we have to subtract those as well, which then becomes plus A dagger I, AK, A dagger J, AL, which then gives the Hamiltonian in second quantization as basically one particle operator that remains, and then the two particle operator, we take the expectation value of any two pairs that we can make, and sometimes you have to commute first before you can make that pair, and then we have to subtract the zero energy to make sure that we get down to the same energy as we started before. Next semester we will rederive the Hartree Fock approximation diagrammatically, and then this form will come out as the Hamiltonian that we are looking at. But I did want to give it here to you so that you see, when you recognize it, when you see this Hamiltonian as, hey, that is the Hartree Fock Hamiltonian, which you get to when you just minimize the energy for a state that can be represented as a single Slater determinant eigenstate. Thank you very much for your attention. We see each other in the next video. Stay healthy.